So welcome to the second part of MA 103 Introduction to Abstract Mathematics. So the first 5 weeks of the Lent term will be given by me, and so far in the Michaelmas term there were two parts. In the first part you learned about some things about sets, functions and logic, and the last 5 weeks of Michaelmas term, which were given by me, were on analysis, where we learned some fundamentals. We started with the real numbers and the least upper bound property of the real numbers. Then we learnt about sequences and their convergence. And finally, we learnt about the continuity of functions and the properties of continuous functions. Now, in the Lent term, again, the term is divided into two halves. The first part, which will be given by me, the first 5 weeks, will be on chapters 4 and 5 of my lecture notes. First, we will talk about number systems, and starting with natural numbers, we will construct the integers, the rational numbers, and finally the real numbers, and we'll also discuss some other things like cardinality. And then chapter 5 will be on the set of integers with its two operations, addition and multiplication, and we'll explore the structure that one gets there and talk about things like divisibility and prime numbers and so on. And then the last 5 weeks will be on groups and vector spaces, but only the first 5 weeks will be given by me. The plan in the first 5 weeks of Lent term is to cover chapters 4 and 5 from the lecture notes for my part. Chapter 4 is on number systems, and starting with the natural numbers, we'll construct the set of integers, the rational numbers, and finally the real numbers. And along the way, we'll prove some of the properties that we have been taking for granted. And in this chapter, we'll also learn some auxiliary things such as the rational zeros theorem and discuss cardinality. Then in chapter 5, we'll focus a bit more on this set of integers with its two arithmetic operations of integer addition and multiplication and the structure which is then formed, which is the structure of a ring. So we'll see what that means. And we'll talk about things such as the division algorithm, the greatest common divisor, prime numbers, and we'll prove the fundamental theorem of arithmetic. And the chapter will end with a discussion of modular arithmetic and a ring, which we will denote by Zn. So we'll now begin with chapter 4, which is on number systems, and as I mentioned, we will start with the natural numbers and construct the set of integers, the rational numbers and real numbers, and we will also develop their arithmetic along the way and prove properties of this developed arithmetic. We will also prove things like the trichotomy law for the order relation along the way. So fundamental in all this development is going to be the notion of equivalence relations. And equivalence relations you have met earlier, but let us begin with a recap of this so that we refresh our memory. So first of all, what is a relation? So let S be any set, and S times S denotes the Cartesian product of S with itself, and this is the collection of all ordered pairs A, B, where A and B belong to the set. Now any subset R of this Cartesian product of S with itself is called a relation. And if an ordered pair A, B belongs to this relation, then we write ARB, and this can be read as A is related to B. So let's consider a few examples of relations. So let S be the set of all human beings, and we introduce this relation R sibling, and this is the subset of S times S, comprising all pairs of human beings A, B, such that A and B have the same biological parents. So if I take any human being A and you look at the ordered pair A, well, A has the same biological parents as A. So you can consider yourself to be your own sibling. Okay, so we allow that. And let's consider another example. Let's take S to be all the straight lines in the plane and consider this relation R parallel. So this is the collection of all pairs of lines L1, L2 such that L1 is parallel to L2. And here we accept the fact that any line is parallel to itself. Okay, so this is also a relation because it's a subset of the set of all pairs of lines. As our third example, let's consider the set S to be the set of all integers, and let's consider this parity relation, R parity, and it's the collection of all ordered pairs A, B of integers such that 2 divides their difference. So for example, the ordered pair -1, 1 belongs to this parity relation because the difference of these two will be minus 2 and 2 divides minus 2. 2 times minus 1 is equal to minus 2. So we know that a relation on a set S is simply a subset of S times S, but for a relation to qualify as an equivalence relation, it has to satisfy something more. So let's recall the definition of an equivalence relation. So let S be a set, then a relation R on S is said to be an equivalence relation if it is reflexive, symmetric, and transitive. Reflexivity means that for every A in the set S, you have that A is related to itself. Symmetry means that for every A and B in S, such that A is related to B, we have also that B is related to A. And transitivity means that whenever A, B, and C are in S, such that A is related to B and B is related to C, we have that A is related to C. So let's see some examples and let's revisit the three relations that we have just looked at: the sibling relation, the parallelity relation, and the parity relation. And let's check that each of these is an equivalence relation. So for the sibling relation, is it reflexive? And the answer is yes, because for every human being A has the same biological parents as A. So it's reflexive. The relation is also symmetric because whenever A and B are two human beings such that A has the same biological parents as B, then B has the same biological parents as A. So the relation is also symmetric. And it is also transitive because whenever you have human beings A, B, and C, such that A has the same biological parents as B and B has the same biological parents as C, you have that A has the same biological parents as C. So the sibling relation is reflexive, symmetric, and transitive, so it's an equivalence relation. Now let's revisit the R parallel relation. So we have that every line is parallel to itself, so the relation is reflexive. Whenever you have two lines A and B in the plane such that A is parallel to B, then B is parallel to A, so the relation is also symmetric. And finally, if you have three lines A, B, and C such that A is parallel to B and B is parallel to C, then A is parallel to C. So the relation is also transitive. So the relation is reflexive, symmetric, and transitive, and so it's an equivalence relation. Finally, let's look at the parity relation. So first of all, if you have any integer A, then A is related to itself because when you look at A minus A, you get 0 and 2 divides 0. Moreover, it is symmetric because whenever 2 divides A minus B, 2 also divides B minus A. And finally, the relation is transitive because if you have three integers A, B, and C, such that 2 divides A minus B and 2 divides B minus C, then 2 will also divide A minus C. To see this, we note that A minus B is 2m for some integer m and B minus C is 2n for some integer n. And so if you add these two, the B cancels and you get A minus C is 2 times m plus n, and so 2 divides A minus C. So why are we interested in equivalence relations? And the answer is when you have an equivalence relation on a set, then it partitions the set into equivalence classes. So what are equivalence classes? So let S be a set with an equivalence relation which we denote by tilde. Then for each element A of the set, the equivalence class containing A, which we denote by this symbol, A in the square brackets, it's the collection of all the elements B in S such that A is related to B under this equivalence relation. So if we revisit the examples that we have been considering and take for example the sibling relation, then the equivalence class containing U is the set containing you and your biological brothers and sisters. If you look at the R parallel relation and you take a straight line L, then the equivalence class containing that straight line is the set of all those lines L prime such that L is parallel to L prime. So as a final example, let's consider the R parity relation and let M be any integer and let's show that the equivalence class containing M is the set of all integers k, which can be written in the form m minus 2n for some integer n. So if I take any k in here, then we see that m is related to that k because when you do m minus k, you get 2n, which is divisible by 2. So any k in here belongs to this equivalence class, and vice versa. If you take a k which belongs to this equivalence class, that means that m minus k is divisible by 2, so you can write it as 2n for some integer n, and by rearranging you see that k is actually m minus 2n for this integer n, and so also any element in the equivalence class belongs to this set. So both inclusions are true, and so we have that the equivalence class containing m is precisely this set. So we'll now prove the following theorem about equivalence classes. So let S be a set with an equivalence relation tilde and A and B be any two elements of the set. Then our first claim is that A is related to B if and only if the equivalence class containing A is equal to the equivalence class containing B. And the second claim is it's not the case that A is related to B if and only if the equivalence class of A intersected with the equivalence class of B is empty. In other words, these two equivalence classes are disjoint. So let's prove the first claim first. So there are two implications here. We first have to show that A is related to B implies that the equivalence class of A is equal to the equivalence class of B, and vice versa. Starting from this statement, we have to end up with this statement. So let's first prove this way implication. So we assume that A is related to B, and we have to show that the equivalence class containing A is the same as the equivalence class containing B. Now both of these are sets, so we have to prove the equality of two sets. So we'll show that one set is included in the other and vice versa. So let's start with any x in this set. So x is in the equivalence class containing A. What does that mean? That means that A is related to x. But since A is related to B, by symmetry we also know that B is related to A. So we know that B is related to A and A is related to x, and so by transitivity these two imply that B is related to x, which means that x belongs to the equivalence class containing B. So we started with something in the equivalence class containing A, and we showed that that element is also in the equivalence class containing B, and so we have that the equivalence class of A is contained in the equivalence class of B. So we have proved one inclusion, and now we have to show the other inclusion. So suppose that X belongs to the equivalence class containing B. What does that mean? That means that B is related to X. But we also know that A is related to B. So A is related to B, B is related to X, which means by transitivity that these two give that A is related to X. So this means that X belongs to the equivalence class of A. So we started with something in the equivalence class of B, we ended up by showing that that same element is in the equivalence class of A, and so also the equivalence class of B is contained in the equivalence class of A. So since both of these sets are included in each other, it follows that these two sets are the same. So we managed to prove this implication in statement number 1. Now we have to prove that if the equivalence class of A is equal to the equivalence class of B, then A is related to B. Well, if the equivalence class of A is equal to the equivalence class of B, let's first note that B belongs to the equivalence class of B, because by reflexivity we know that B is related to B. So B belongs to the equivalence class of B, but the equivalence class of B is the same as the equivalence class of A, so B belongs to the equivalence class of A. But that means that A is related to B, and so we have got this. So we have managed to prove the first statement. So now let's prove the second claim, which says that it is not the case that A is related to B if and only if the intersection of these two equivalence classes containing A and B is empty. So we first note that if X is in the intersection of these two equivalence classes, then X belongs to the equivalence class containing A, so that A is related to X, and X also belongs to the equivalence class containing B, and so B is related to X. But if B is related to X, then by symmetry X is related to B as well. And now let's look at these two. A is related to X, we know, and X is related to B. So by transitivity then A is related to B. So what we have managed to show is that if X belongs to this intersection, so that this intersection is not empty, that implies that A is related to B. And the contrapositive of what we have just shown is the fact that if it is not the case that A is related to B, then it's not the case that this happens. In other words, the intersection of the equivalence class of A with the equivalence class of B is empty. And so we have shown the implication that if this is true, then this is true. Now let's prove the reverse implication. To do that, let us suppose that A is related to B. But then by the first part we know that the equivalence class of A and the equivalence class of B are the same. But we know that A is related to A by reflexivity, and so A belongs to the equivalence class containing A, but that we know is the equivalence class containing B. So this A belongs to both the equivalence class of A and the equivalence class of B, so it belongs to that intersection. So the intersection is not empty. So what we have managed to show is that if A is related to B, then this intersection is not empty. And the contrapositive of this statement is precisely that if it is not this case, then it is not this. In other words, if the intersection of A and B is empty, then it implies that this cannot happen. In other words, it is not the case that A is related to B. And so we have shown that this statement also implies this statement. So this completes the proof of this theorem. So if you have an equivalence relation on a set, then we note that S is the union of all the equivalence classes, and this is because, well, any equivalence class is of course a subset of S. So if I take the union of all the equivalence classes where the A runs over S, then we get a subset of S, and vice versa. If A is an element in S, then it belongs to its own equivalence class, and so certainly to this union, and so any element in S is contained in here. So S can be written as the union of all these equivalence classes. Moreover, any two equivalence classes are either exactly the same if A happens to be related to B, or if it is not the case that A is related to B, then they are completely disjoint. And so this S is partitioned into these equivalence classes. So you get sort of these rooms separated by walls, and in each room you have exactly an equivalence class, and all the elements in there are related to each other by that first statement of the theorem that we just proved. So the equivalence classes partition S, and roughly speaking you can think of this equivalence relation as sort of a generalized equality, and then all the elements of an equivalence class are basically elements which are equal to each other under this equivalence relation. So as examples, let's revisit our three relations. For the sibling relation on the set of all human beings, we have that this set is partitioned into equivalence classes, and each equivalence class looks like this. You have a person and all the siblings of that person. If you look at the relation R parallel, the set was the set of all lines in the plane, and this is now partitioned into equivalence classes, and each equivalence class looks like this. It's a line and all the lines which are parallel to it. And finally, for the parity relation on the set of all integers, you have only two equivalence classes: the equivalence class containing 0, which gives rise to the even integers, and the equivalence class containing 1, which comprises all the odd integers. So having recalled what equivalence relations are, we now start with our program of constructing the number systems, and we start with the natural numbers. Now when we think of the natural numbers, we mean the counting numbers 1, 2, 3 and so on. And the idea of counting is that, well, you start from 1, and we know that for every natural number n there is a next one or a successor. But if we ask ourselves how do we build the natural numbers, then a naive answer would be that you start with 1 and take successors one after the other. But mathematically, what do we mean by the construction of natural numbers? Well, in mathematics, we want to rely on sets and functions. So Peano formulated axioms for the natural number system in 1889 using only the mathematical language of sets and functions. So that's where we will begin, by learning what these axioms are. So here are the Peano axioms for a set n and a successor function sigma from n to n. So we say that a set n and a successor function sigma from n to n satisfy the Peano axioms if the following three statements hold. The first statement says that the set n contains a special element which we denote by 1, such that for every n belonging to the set, you have that 1 is not equal to sigma n. So in other words, 1 is not the successor of any natural number. So if you look at the element 1 over here in the codomain, then that does not belong to the range of this function. It does not belong to the image of this function. That's the first demand. The second demand is that this sigma is injective, so that whenever you have n and m belonging to the domain such that n is not equal to m, their images are also not equal to so sigma n is not equal to sigma m. And the contrapositive of this is that if the images are the same, so if sigma n is equal to sigma m, then n is equal to m. And the third demand is what we call the induction axiom, and that says that if you have any subset S of n which has these two properties, that 1 belongs to the set, and whenever n belongs to the set, its successor also belongs to the set, then this set S is the whole of n. Okay, so these are the Peano axioms, and then the terminology is that this sigma n is called the successor of n, and we think of this n as the set of all natural numbers. So you have 1, the special element 1, and then its successor is what we define 2 to be, and then the successor of 2 is what we define 3 to be, the successor of 3 we define as the natural number 4, and so on. So this is the axiomatic development of the set of natural numbers. So once we have a set n and a successor function such that the Peano axioms are satisfied, then we think of n as the set of natural numbers. But it is a natural question to ask, does there exist such a set and a successor function so that the Peano axioms are satisfied? And the answer is yes, but this construction is beyond the scope of this course. But nevertheless, we make a little remark. So the question we are asking is, does there exist a set n and a successor function so that the Peano axioms are satisfied? And the answer is yes. And since we want to construct everything using sets, here is one possible construction. As 1, you take the set containing the empty set. As 2, you take 1, which is a set, union the set containing 1, and then you get this set. And as 3, you take 2, union the set containing 2, and then it turns out that you get this set, and you continue this process. And then sigma of n, so n is going to be a set, is defined to be n union the set containing n. And then it turns out that this construction makes the set that we get together with the successor function satisfy all the Peano axioms. So a construction is possible, but it is cumbersome. And moreover, to explain what this and so on means, utilizes the axioms of set theory, and that we will not do in this first course. So for us, we will simply assume that there exists a set n and a successor function so that the Peano axioms are satisfied, and then we think of this set as the set of all natural numbers, and then we will use this successor function to develop addition of natural numbers and multiplication of natural numbers, and the rest of this section will be on proving the properties using the Peano axioms. Okay, so to reiterate, we take for granted that there exists a set n and there exists a function sigma from n to n which satisfy the Peano axioms, and then n is called the set of natural numbers and this sigma is called the successor function. And then the plan is to prove the properties of natural numbers using this setup. So we will define addition using the successor function, multiplication using the successor function, and we'll prove their properties such as commutativity and associativity by relying on the Peano axioms, and we will also explain what is the order relation on n. So here is our first result. We know that 1 is not the successor of anything, but now we'll show that every other natural number is the successor of some natural number, and then that natural number will be called a predecessor, meaning the one before. So here is the precise statement of the theorem. It says that if n is any natural number which is not equal to 1, then this n is the successor of something. So there exists an m in n such that the successor of m is this n. And then this m is called the predecessor of n, namely the number just before n. And we then know that this predecessor must be unique because this sigma is injective. So to prove this, we will consider the following set, which is the union of the set containing 1 and the set of all successors. So this is the set of all k's such that k is the successor of something. So there exists some m in n such that sigma of m is equal to k. Now we notice that this is a disjoint union. This 1 does not belong to this blue part because it is not the successor of anything because of one of the Peano axioms. So to prove our theorem, we'll show using the induction axiom that this S is the whole set of natural numbers, and that will prove this theorem because if I take a natural number which is not equal to 1, then it belongs to this S but is not equal to 1. So not in this part, but in fact it belongs to this blue part, and hence it will be a successor. So we want to show that S is equal to n. So to prove this, we will use the induction axiom. So what we have to show is that first of all 1 belongs to this set, and moreover that whenever n belongs to the set, also the successor belongs to the set. Well, 1 clearly belongs to the set because S is the union of the set containing 1 plus extra stuff. And now let's prove the claim that whenever n is in S, its successor is also in S. Well, if n is in S, this S is a collection of natural numbers, right? So this is a subset of n. But now when I take sigma n, well, that is a successor of what? Of n. So it belongs to this blue part. Well, if it belongs to this blue part, it is certainly in S. So sigma n, being a successor, belongs to S. So this proves this claim. And since 1 belongs to S and whenever n belongs to S, also we have that sigma n belongs to S, it follows by the induction axiom that this S is the whole set of natural numbers. So whenever I take a natural number which is not equal to 1, then since this n is equal to S, this is exactly an n which is in S but is not equal to 1. And since this was a disjoint union, well, if it is not 1, it has got to belong to this blue part. In other words, it's a successor of something. So there exists some m in n such that n is the successor of this m. So this proves this theorem, which says that every natural number which is not equal to 1 is the successor of some natural number. Okay, so the next task is that we are going to define addition and multiplication of natural numbers and prove their properties such as commutativity, associativity, and so on. And the way addition and multiplication are going to be defined is by giving a recursive definition. So I want to say something about that. So again, this is a remark which is not really part of the course, and this remark is on recursive definitions. So it turns out that using the Peano axioms, it can be shown that to specify a sequence of objects C1, C2, C3 and so on, which are indexed by the natural numbers. So these objects needn't be numbers, they can be some mathematical objects. They can be sets or they can be functions or whatever. Okay, so to specify such a sequence of objects which is indexed by n, it turns out that it is enough to specify the first object and then a rule for obtaining from Cn C sigma n. So once you know what Cn is, you also know what the object corresponding to the successor of n is. So once you know this, then this determines the whole sequence. Now this is intuitively quite obvious because if you know C1, then from this rule you can deduce C2. Once you know C2, then you can deduce C3 and so on. So this is intuitively fairly obvious. But a proof of this can be given that from the Peano axioms you can prove this, that whenever you want to specify such a sequence, it's enough to specify the first object and a rule for determining C sigma n knowing Cn. Now, how could a proof work? We could try our hand at it. We could, for example, consider the set S of all those natural numbers such that this star determines all the objects up till n. Okay, so you take all those n such that the star has already determined C1 all the way up till Cn. And then using the induction axiom, we can try to prove that S is equal to the whole set of natural numbers. Well, 1 clearly belongs to the set because star indeed determines C1, no problem. And also whenever n belongs to S, What does that mean? That means that star has already determined C1 all the way up till Cn, but once you know Cn, you also know C sigma n. So in fact, star has determined C1 all the way up till C sigma n. So C sigma n also belongs to the set. And so by the induction axiom, it would follow that S is equal to n. Isn't this a proof? And the answer is not really, because we have used this less than or equal to. What does that mean? We have not yet defined what is this order relation on the set of natural numbers. Well, it turns out that since this is not yet defined, this is not admissible in this proof. So this proof is not alright, but a different proof can be given. But that proof is a bit technical, so we will not cover that in this first course. And so we'll accept recursive definition because it's fairly intuitively obvious that if you have C1, then from this rule you know C2, once you know C2 you know C3 and so on. Alright, so that was the end of this remark, and again this is not part of the course. So we are now ready to define the addition of natural numbers, and this will be done recursively. So first we'll explain what is n plus 1, and then knowing n plus m for some natural number m, we will also explain what is n plus the successor of m. So first of all, for any natural number n, you have that n plus 1 is defined to be simply the successor of n. And knowing n plus m for some natural number, n plus the successor of m is defined to be the successor of whatever n plus m was. So let's see an example. We want to find out what is 2 plus 2. Well, 2 here is actually the successor of 1. So 2 plus 2 is really 2 plus the successor of 1, right? But 2 plus the successor of something is simply the successor of 2 plus whatever thing was there over here, that was 1. So 2 plus the successor of m will be the successor of 2 plus m. M here is 1. So 2 plus the successor of 1 is simply the successor of 2 plus 1. But 2 plus 1 from here, 2 plus 1 is the successor of 2. So this 2 plus 1 is the successor of 2, which we have called 3. So what we have got is that 2 plus 2 is the successor of 3, and that's what we define 4 to be. So 2 plus 2 is equal to 4. Okay, so now having defined addition, we can prove the properties of addition, which we have so far taken for granted, but now we can prove them using these Peano axioms. So here is the theorem, and this says that addition of natural numbers is associative. What does that mean? That means that for all natural numbers L, M and N, you have that if you first add N and M, you get a natural number, and to that you add L. The result is the same as first adding M and L, and then you get a natural number which you add to N. So these two are the same. So let's prove that, and to prove this we will consider the following set. So this set is the set of all L's, which are natural numbers, such that for all natural numbers M and N, you have that N plus M plus L is the same as N plus M plus L. Okay, so we'll show that this set S is the whole set of natural numbers, and to do this we will use the induction axiom. So to use the induction axiom, we will show that first of all 1 belongs to this set, and whenever L belongs to the set, also its successor belongs to the set. So let's start with 1 belonging to S. Why does this L equal to 1 work? Well, what we have to show is that when L is equal to 1, this statement holds. In other words, for all M and N in N, N plus M plus 1 is the same as N plus M plus 1. So let's start with the left hand side, which is N plus M plus 1. This, by the definition of addition, is the successor of N plus M. You see, you have something plus 1, that by definition is the successor of that something. So this is the successor of N plus M. Again, by the definition of addition, this successor of N plus M is nothing but N plus the successor of M. You see, you should read it from here to here. N plus the successor of something is the successor of N plus M, right? So that was the definition of how addition was defined. So because of that, this is true. And now this successor of M is exactly what M plus 1 was defined to be. So this is equal to n plus m plus 1, which is exactly the right hand side. You see, it is n plus m plus l is equal to 1. That's what we are checking, that l equal to 1 belongs to the set. So this right hand side is n plus m plus 1. So 1 belongs to the set. Now let's prove also that whenever l belongs to the set, also its successor belongs to the set. So since l belongs to the set, we already know that this happens for all m and n which are natural numbers. And now we have to prove the same thing, but not for L, but for the successor of L. Okay, so let's start with the left hand side. So it is n plus m plus the successor of L. Now, by the definition of addition, this is the successor of n plus m plus L, right? Because something plus the successor of L is the successor of that something plus L, right? So that's exactly what has happened here. Now, since L belongs to S, we know that n plus m plus L is the same as n plus m plus L. That's exactly what this is. When L belongs to S, this holds, right? So because of that, this inner thing is the same as this thing. Now, the successor of n plus something is n plus the successor of that thing, again by the definition of addition. So because of that, we have this thing, and this sigma of m plus L you can write as m plus the sigma of L, again by the definition of addition. After all, what is m plus the successor of L? It's the successor of m plus L, right? So because of that, these two are equal. This is exactly what the right hand side is. You see, it is n plus m plus the successor of L, right? So it follows that for all natural numbers n and m, you have n plus m plus the successor of L. We have managed to show is n plus m plus the successor of L. So this sigma L also belongs to the set. So we have shown that whenever L belongs to S, its successor also belongs to S, and so by the induction axiom, it follows that S is the whole set of natural numbers. So what does that mean? That means that for all L which belongs to N, well, it belongs to S. So we know that for these L's, no matter which m and n you take in N, you have that n plus m plus L is the same as n plus m plus L. So we have got that for all L, m and n plus m plus L is the same as n plus m plus L. So this shows the associative law. Let's prove that the addition of natural numbers is also commutative, by which we mean that for all natural numbers n and m, n plus m is the same as m plus n. Now we will first prove this when m is equal to 1. So that's part 1. We will show that for every natural number n, n plus 1 is the same as 1 plus n. Okay, so let's prove that. So to do this, we will consider the following set. S is the set of all those natural numbers for which n plus 1 is the same as 1 plus n, and we want to show, of course, that S is the whole set of natural numbers. So to do this, we will use the induction axiom. So we want to show that 1 belongs to the set, and whenever n belongs to the set, also its successor belongs to the set. So let's first see why 1 belongs to S. Well, to belong to S, this should happen. So 1 belongs to this set because when you look at this left hand side, that's 1 plus 1, that's the successor of 1, and that's of course the right hand side, 1 plus 1. So 1 trivially belongs to the set. And now suppose that n belongs to the set, and we want to show that its successor belongs to the set. Okay, so we want to show that sigma n plus 1 is 1 plus sigma n. So let's start with the left hand side. That's sigma n plus 1. Now the sigma n is really n plus 1 by the definition of addition. So you get n plus 1 plus 1. Now since n belongs to the set, yeah, because that's what we are assuming, so this n plus 1 is actually equal to 1 plus n. So you get 1 plus n plus 1. But associativity we have already proved. So this is actually 1 plus, and I put the brackets around here. So you first do n plus 1. Now this n plus 1 is sigma n, again by the definition of addition. And so we have got that sigma n plus 1 is 1 plus sigma n. So sigma n also belongs to this set. So we have managed to show that whenever n is in S, its successor is also in S. So by the induction axiom, it follows that S is equal to n. In other words, for all the natural numbers, n plus 1 is 1 plus n. Now I want to prove this for all m's, and so far I have only proved it for m equal to 1. So here is the second part. Now I consider the set S prime comprising those m's such that for all n's, n plus m is equal to m plus n. Okay, and so far I know that 1 belongs to S prime. That was the part 1, because indeed for every natural number n, n plus 1 is equal to 1 plus n. So this statement holds with m equal to 1, and so 1 certainly belongs to this S prime. Now we'll show that whenever m is in S prime, its successor is also in S prime. So we have to check this basically. Knowing that m belongs to S prime, we have to show that this also works with sigma m instead of m. Okay, so let's look at this left hand side. So let n be any natural number, and let's look at this left hand side. So that's n plus sigma m, and that by the definition of addition is the successor of n plus m. But since m is in S prime, we know that for any natural number n plus m is the same as m plus n. So this inner thing n plus m is the same as m plus n, and so these two are the same. Now the successor of m plus n is really m plus the successor of n, again by the definition of addition, and the successor of n is n plus 1. So you have ended up with m plus n plus 1. But again by part 1 we know that n plus 1 is the same as 1 plus n. So we have that this is the same as m plus 1 plus n. And again we use associativity. So this is m plus 1 plus n. And m plus 1 is the same as sigma m, the successor of m by the definition of addition. And so you have ended up with sigma m plus n, which is the right hand side here with m replaced by sigma m. So we have got that for every natural number n, n plus sigma m is sigma m plus n, and so sigma m also belongs to S prime. So whenever m is in S prime, sigma m is also in S prime. So we know that 1 belongs to S prime, and whenever m is in S prime, its successor is also in S prime. So by the induction axiom, this S prime is the whole set of natural numbers. What does that mean? That means that no matter which natural number m you take, we have this holding. So for every natural number n, n plus m is the same as m plus n. So we have, reading this last statement, that for every m and every n natural numbers, n plus m is the same as n plus n, which is the commutative law of addition of natural numbers. So next we define multiplication. So this will be denoted by this symbol times, and the definition is again recursive. So we first define for any natural number n, n times 1, and that's simply defined as n. So you're taking n sort of 1 times, so that's equal to n as usual. And knowing n times m for natural numbers n and m, let's define what is n times the successor of m. So sort of intuitively here n is taken m times, and here now it's taken m plus 1 times. So this is basically n taken m times, and then you add n to it, right? And that's why we define n times the successor of m is n times m, which we know, and then you add n to it. Okay, so this is how multiplication is defined recursively. You first define n times 1, and then knowing n times m, you're saying what n times the successor of m is. Okay. Alright, so as an example, let us prove this mini theorem, which says that for all natural numbers n, 1 times n is equal to n. Of course, by definition, n times 1 is equal to n. Okay, but as yet we don't know the commutativity law, so we cannot just say 1 times n is the same as n times 1, which is equal to n. So this needs a proof, and what we will do is use the induction axiom on this set S. So let S be the set of all those natural numbers for which this works, that 1 times n is equal to n. And the task is to prove that this S is the whole set of natural numbers. Okay, so to do this we will use the induction axiom. So we have to check that first of all 1 belongs to the set, and whenever n belongs to the set, its successor also belongs to the set. First of all, does 1 belong to the set? Well, to belong to the set, you should have this property. So let's see if I take n equal to 1, does this work? Well, what's 1 times 1? N times 1 is equal to n by definition. So 1 times 1 will be 1. Well, so 1 times 1 is equal to 1, and that's exactly this equation, right? So 1 does belong to S. And now let's suppose that n belongs to S, and the task is to show that its successor also belongs to S. Okay, so for the successor to belong to S, we should have this happening with n replaced by sigma n. So let's start with the left hand side. So 1 times sigma n, well, whenever you have 1 times sigma m, that by definition is this. So now we have n is equal to 1 as over here, and the m is equal to n, right? And so by definition, 1 times sigma n will be, n is 1, so 1 times m is n, and so 1 times n, and n is 1, so you get a plus 1 here. So using the definition, you have that 1 times sigma n is 1 times n plus 1. Okay, that's why I've written multiplication definition over here. But 1 times n is equal to n because n belongs to S, right? So that's our assumption, that n belongs to S, and then 1 times n we know is equal to n. So this 1 times n is equal to n, and we have ended up with n plus 1, but that's the successor of n by the definition of addition. So we have got that 1 times sigma n is equal to sigma n, which is exactly this with n replaced by sigma n. So sigma n belongs to S, and we have managed to show that whenever n is in S, also its successor is in S. So by the induction axiom, it follows that S is the whole set of natural numbers. In other words, for every natural number, you have that 1 times n is equal to n. Okay. So as the final theorem for today, let us prove that multiplication of natural numbers is commutative, by which we mean that for every n and m natural numbers, you have that n times m is the same as m times n. So to prove this, we will first prove a lemma, which is this claim over here, which says that for any two natural numbers m and n, m plus 1 times n is equal to m times n plus n. So let's consider this set S, which is the collection of all natural numbers n, such that for every natural number m, m plus 1 times n is equal to m times n plus n. And to prove this claim, we have to show that this S is the whole set of natural numbers. So we use the induction axiom to do this. We will show that 1 belongs to it, and whenever n belongs to it, also its successor belongs to this set S. So first of all, does 1 belong to S? To show that 1 belongs to S, we have to check whether this statement holds when the n is replaced by 1. So for any natural number m, you have that this left hand side is m plus 1 times 1. Okay, but anything times 1 is the same thing by definition of multiplication, so this is just m plus 1. And this m you can write again using the multiplication definition as m times 1. So you have got m times 1 plus 1, which is exactly this right hand side when n is equal to 1, and so 1 belongs to this set. Now let us suppose that n belongs to this set, and we want to show that its successor also belongs to the set. Okay, so then we have to check that this statement holds when the n is replaced by sigma n. Okay, so let's take any m belonging to n, and let's look at this left hand side with the n replaced by sigma n. So then you get m plus 1 times sigma n, and by the multiplication definition, whenever you have some natural number times the successor of something, then it is equal to this natural number times this inner thing and plus this thing again. So by the multiplication definition, this is m plus 1 times n plus m plus 1. And this part, m plus 1 times n, you can replace by m times n plus n because n belongs to S. So since n belongs to S, we already know this, m plus 1 times n is this thing, and that is the replacement which has taken place over here. M plus 1 times n is exactly this thing, m times n plus n. Now, we know various properties of addition. We know it's associative and it is commutative. So using those two, you can first club this part together, and then you can further bunch n and m together, and using commutativity you can swap the order of m and n. So you get m plus n, and then you can again split them apart and join the m to this one and the n to the other part. Okay, so using all these properties of associativity and commutativity of addition, you have that this is exactly equal to this one, where basically the end result is that the m and n have been swapped. So this is m times n plus m plus n plus 1. Now this thing, again my multiplication definition is m times sigma n. After all, what would be m times the successor of something? It would be m times n plus m, right? Which is exactly this thing. And by the definition of addition, this n plus 1 can be replaced by sigma n. So we end up with this one, which is exactly this right hand side with the n replaced by sigma n. So sigma n belongs to S. So knowing that n belongs to S, we have managed to show that sigma n belongs to S, and we also know that 1 belongs to S. So by the induction axiom, it follows that S is equal to n, and hence we know this for all natural numbers m and n. So that was the first part of this proof, where we have proved this auxiliary lemma, which is going to be used to prove the main task at hand, which is this commutativity property. Okay, so let's see now how to prove this commutativity property. So let S prime be the set of all natural numbers m, such that for every natural number n, m times n is equal to n times m. So using the induction axiom, we will show that S prime is the whole set of natural numbers, and this will prove our theorem about the commutativity of multiplication. So let's first check that 1 belongs to S prime. So to check that, we have to show that this statement holds when m is equal to 1. So for every natural number n, we have that 1 times n is equal to n. That was the example that we just considered. And n is also equal to n times 1 by the definition of multiplication. So we have got that 1 times n is n, which is equal to n times 1, and so it is indeed true that 1 belongs to S prime. Now let us suppose that m belongs to S prime, and we want to show that its successor also belongs to S prime. So then we have to show that this statement holds when the m is replaced by sigma m. So for n belonging to n, we have that this left hand side with the m replaced by sigma m is sigma m times n. And by the addition definition, this sigma m is m plus 1. And by the claim that we just proved by this lemma, we have that m plus 1 times n is m times n plus n. And since m belongs to S prime, we already know that m times n is n times m. So this can be replaced by n times m. And by the multiplication definition, n times sigma m is exactly what this is, because that will be n times m plus n. So this is equal to this. So we have ended up with sigma m times n is the same as n times sigma m. So this sigma m also belongs to this S prime. So by the induction axiom, it follows that S prime is equal to n, and this proves this theorem about the commutativity of multiplication. And as exercises, we will also see that this multiplication is associative, and moreover multiplication together with addition has this distributive property, okay, that for all natural numbers n, m and l, n times m plus l is the same as n times m plus n times l. So it's this multiplication is distributing over this addition. You first do this and then you add to it n times l.